see if I can finish this problem we started last time. So let me go back to that. Where is the thing? Oh, is it there? I still have this. Okay. Come on. Okay, why can't I change the screen size? What is going on here? Is this thing frozen? Let's try it again. No? Okay, it's not responding. What the hell? Why is it not doing anything? It's frozen. Why is it frozen? Just start over. If I clear the canvas. Oh, it's not zooming. It doesn't want to zoom at all. Okay. That's gonna be a problem. Let me get rid of it. Let's see if I can just delete the task. Zoom going. Okay. No, maybe. No. All right. Oh, why is it not working? What if I do this one? Maybe this will work. I guess we could try this one. I don't know how this one works. All right. Well, okay. I don't know. I'll try this. This is weird. All right. Well, okay. So we were doing this problem where we had the oh, really? Come on. Don't do this. Why is it not? It's not good. Oh, this is terrible. Okay, whatever. So we had the a shaft that was supported at 2 points, right? And then had a dead load at the end due to a pulley of 6 kilonewtons. And we were trying to find the beam deflection by direct integration, right? So the beam is going to be pinned at points A and B. And so it's going to do something like that, right? So where we stood on this, oh, and I cannot scroll this. Oh, this is not good. Geez, really? I don't know how to do this. I don't know how to do this then. How do I have no. Okay, I'm going to restart my computer. I'm sorry, guys. I don't know. This is not working at all. Okay, I'll be back in like 2 minutes. All right. I hate this shit. Look at this. All right, I think I'm back now. Let's try this again. All right. No, don't start Teams. Come on, don't do that to me. Okay, so the problem where we stood last time was we got the shear and the moment diagram, right? So it's about the loading of the beam was let's see if I remember what it was. So it's acting on this. We had 3,000. Wait, what are the units of this? Kips, right? Kilonewtons. So 3 kilonewtons at point A, right? Then we go over 2 meters to point B. And we had a reaction force there of 9 kips, 9 kilonewtons. And then where the pulley was is the down force of 6 kilonewtons, right? So the way this beam was, we had supports here at A and B, right? And then the pulley was at point C, I believe, right? Yeah. Okay. So this gave us a shear diagram that looked as follows. We had a negative shear of 3 kilonewtons going from A to B. Then it jumped up to 6 kilonewtons and then back down to 0 at point C, right? So this is 6 kilonewtons of shear and then minus 3 kilonewtons of shear there, okay? And then the moment diagram, so that's the shear diagram, and then the moment diagram looked as follows. Here's X, and then here's the moment. So we had 0 moment at point A as well as point C. And then obviously the moment curve goes down with a slope of negative 3 kilonewtons until we get to point B. And then goes up with a slope of 6 kilonewtons here, right? So this is 6 Oops. That was the slope here, and the slope here is -3 kilonewtons. So that means that the value of the moment down here at point B is going to be -6 kilonewton meters, right? Okay. So next we were going to take this and then integrate and get the slope, right? So remember that we had the derivative of the slope is equal to m on EI, right? And we have the moment diagram here, so we just need to do the integration. So let's just multiply by EI. All right. Or if we want to integrate both sides, right, you can get that EI times theta is equal to the integral of the moment, oops, dx. All right. So I think what we did last time too is we were able to analytically get that the moment, if you will, right, the moment as a function of x from the diagram up here is as follows, right? From point A to B in that region, the moment curve is -3 x, and that's from x. I'm going to drop the units on here just to make it a little bit easier, but obviously all the forces are kilonewtons and the lengths are all meters, okay? So this is going to be from x between 0 and 2 meters, all right? Then from point B to point C, we get 6x -18, correct? Right, 6x -18, and that's from 2 to 3 meters, right? So if you put in, you can see here we have continuity at point B. So if you put in x equal to 2 into either evaluations, right, you get the -6, correct? If I did that right. So 6 times 2 is 12, -18 is -6, -3 times 2 is -6, right? And then, of course, for the second half of the moment curve, this bit here, if we put an x equal to 3, it goes back to 0, right? So yeah, so there you go. So that's our moment, right? So now if we were to integrate that or get the antiderivative, right? The antiderivative, what does that give us? That's going to give us, all right, -3x squared over 2, right? Plus an integration constant, all right? And likewise for the second bit, now that's going to be from 0 to 2. And then if we integrate the second one, we're going to get 6x squared over 2, or 3x squared minus 18 times x plus another integration of constant, another integration constant. I'm going to call that, let's call this C0 and C1. That's what I did last time. C0, C1. All right. And that's from 2 to 3. Okay. So we did one integration, but we have two integration constants. And the reason why we have that is because we actually still have to have continuity in the slope at point B. So the slope curve, theta of x, is continuous everywhere, and obviously it's continuous at B. So that means that the slope, all right, at 2 just from the minus has to equal the same evaluation to the right, okay? So this is a continuity condition, and that's going to allow us to give us of the relationship between these two integration constants. So in fact, when we do one integration, we really just get one integration constant, all right? Okay, so let's do that. So we're gonna invoke this continuity. So from the left, we're gonna use this equation here. So that's gonna give us minus 3 times 2 squared, that's 4 over 2, so that's minus 6 plus C0, right? 6, right? And that has to equal the evaluation to the right. So that's the second equation evaluated at 2. So we get 4 times 3 is 12 minus 36 plus C1, right? So this is minus 24, right? And then if we were to add 6 to both sides, you get that C0 equals C1 minus 18. Okay, so we don't know C1 and C0, but at least we know that C1 is related to C0 as follows, right? So this, like, let's stick this back into here and then rewrite it, okay? So what do we got? We got now that this is actually going to be theta of x times EI, because we still didn't divide by EI yet. And that is going to equal the following, okay? So that's going to give us, what's the easiest to do? Well, if I put it for C1, yeah, it doesn't do any good, does it? C1 is 18. And maybe that looks, if I wonder if that looks a little bit nicer. If I put in C1, let's try C1 equals C0 plus 18, right? And that way I'll get the 18s at least in the bottom equation, at least I can pull that out for whatever it's worth, okay? So upstairs we get minus 3 halves x squared plus C0, so that has not changed, right? And then downstairs, right, I get still the 3x squared, right? And then I got a minus 18x plus 18. So we can put into there minus 18x minus 1. Or maybe it's easier to do it this way. 1 minus x. Plus C0, correct? And that's from 2 to 3, right? Is that right? 18 C0 minus 18x. Right. Okay. So now we have the equation for theta of x, the slope of the deflection curve, right? But it's in terms of one integration constant. And I can't really solve for that yet. What that integration constant solution is going to get deferred to the deflection curve, because there we're going to be able to invoke the two boundary conditions that the displacement at A and the displacement at B are both 0, okay? So, we could also just divide this by 1 over EI, but let's leave it that way. So next, we're going to use the fact that the derivative of the deflection curve with respect to x is equal to the slope curve, right? And we know that also here that the deflection at x equal to 0, which is point A, has to equal the deflection at 2 meters has to equal 0, okay? Because they're pinned. So I'm going to have two conditions here that are going to allow me to solve for the two integration constants, all right? So if we integrate this function again, right, I'm going to get EI times V of x, and that is going to equal the following, right? So if we integrate the equation from 0 to 2 meters, that is going to give us 1/3 So 1/3. So one is that so minus x cubed on 2? Is that right? Yeah, that's right. Minus x cubed on 2 plus C0 times x plus another integration constant. So I'm going to call that B0, and that's from 0 to 2. And then when we integrate the second equation, we're going to get 3x squared. So we get x cubed plus 18x minus 9x squared, right? Plus C0x plus another integration constant. I'm going to call that B1. And that's from 2 to 3 meters, right? All right. So now we have 3 unknowns, C0, B0, and B1. But again, we have continuity. So we know that at x equal to 2, V has to be continuous, right? So the same deal, right? So when we evaluate either this equation or this equation at x equal 2, we have to get the same answer, right? So let's look at that. So we're going to do that first. So minus 3x minus x cubed over 2 at 2 is 8, 4. So that's minus 4 plus 2C0 plus B0 has to equal 8 plus 36 minus 4 times 9 is also 36, right? Minus 36, so that's cool. Plus C0 times 2 plus B1, right? So these cancel out at least. And what do I get here? I can get that. Well, I got, wait. Oh, and these cancel out. That's good. So this is not too bad. So I get B0 equals 12. B1 plus 12, right? I think I get that, right? All right. So, or, well, that's fine. Let's just do it that way. That's cool. And now when we put that back into here, we're going to get the following for the deflection curve. All right. For the first term, we are going to get, we'll stop that, minus x cubed over 2 plus C0x plus B0. So let's put in there plus B1 plus 12. And that's, again, from 0 to 2. And then for the second equation, well, that's just what we get, right? X cubed minus 18x minus 9x squared. I guess I should put it in descending order, so I probably should do it this way. Plus C0x plus B1. Okay, so now we have 2 unknowns, C0 and B1. And now, so now to solve for these, we can use the fact that V at x equal to 0 has to equal V at x equal to 2 has to equal 0 because they're pinned, right? So the deflection there has to go to 0. All right. So what's the easiest way to do this? Well, okay. So let's take this equation. Let's use this one first, right? And so we can plug in 0 into this equation. So we get EI, well, whatever. We get just B1, right? So this one is just going to give me B1 plus 12 equals 0, correct? And if that's the case, that means that B1 has to equal minus 12. Yeah. Okay. And so that now gives us, so now we got B1 equals minus 12. So this actually just becomes the following, right? Because B1's minus 12, that cancels out. And if B1 goes to minus 12 here, well, there's nothing I can do. It just becomes minus 12, right? So there we go. So now we've gotten B12 out of the way. And then let's use the second condition to figure out what C0 should be. So if we take this one and put it in here, I'll use this equation. I could use either or because they're both valid at 2. They should match. But this one's a little easier. So at 2, we get minus 8. So we get minus 4 plus 2C0 has to go to 0, right? And if that's the case, then we know that C0 has to equal 2, correct? And now finally, that's going to give us the end results. So now all the constants of integration are gone. And we get finally V of x equals 1 over EI. And then this bifurcation, we get minus x cubed over 2 plus 2x, and that's from x between 0 and 2 meters. And then, I guess I've been calling this less than or equal to, but it really doesn't matter because it's continuous. And then on the bottom one, I get x cubed minus 9x squared minus 18x minus, plus 2x. So that actually combines with this, right? And gives me minus 16x minus 12. And that's from not 0 to 3, from 2 to 3. All right, so that is the deflection curve, right? So you could plot that out, and that is how much the beam deflects. Oh, I forgot the EI over EI. The problem wanted us to find the deflection at point C, which is where x goes to 3 meters, right? And so for that, we'll just have to plug it into here. So the deflection at 3 is equal to 1 over EI. And we had numbers for that. What do we get for E and I? Well, E is given. I forget what I calculated I. Let me do that real quick. E is 200 gigapascals, right? So E is 200 gigapascals. And then I, what is I? Let's calculate it. 100 millimeter diameter shaft, right? So that means 1. It's J, we'll divide it by 2 to get I. So I is 4.9 to the minus 6, 4.91. Let me put units on here just to be careful. I'm being a little sloppy here. Let me do my units. I'm going to call this, I know it's to the 9th pascals. I'm going to use to the 6th kilopascals, and you'll see why later on, right? And then for I, it's the 4.91 to the minus 6th, right? And that's meters to the 4th. And then that gets multiplied by this equation evaluated at x equals to 3 meters. 3 cubed minus 9 times 3 times 3 is 9 again, minus 16 times 3 minus 12. Okay, so this well, yeah, we should end up with meters, right? So this has units of, let's just be a little careful on this, right? So obviously there's going to be force upstairs. So let's talk a little bit about that because I did drop the units, right? So what's the easiest way to see that? Right, so okay, let's look at it here, right? So this is a moment, right? So these X is in meters, and then so that means 3, the units for these coefficients is going to be a kilonewton, right? They're going to be force, because then when I multiply that by meters, I get the units that I needed for my moment curve, right? So the coefficients have units of kilonewtons, right? And so that means if we go down here, right, this is a, is that right? No, I have to be careful about this, right? The leading coefficients kilonewtons. So, right. So this unit, yeah, that's what happens whenever I drop the units on this. Well, okay. So EI is out in front of all that stuff. So wait. So moments we're here. So here we're kilonewtons, right? This, the 18 here is kilonewton meters, right? This is again is kilonewtons, right? So then when we integrate, right, what we're going to get is everything gets bumped up by another meter, right? Is that right? What am I doing? I'm doing this wrong. This has to be kilonewtons per, no, that's kilonewton meter, right? And then when we integrate, delta X on there. So EI as units of force per length squared, force times length squared, right? So it's going to be kilonewtons meter squared is EI, right? Kilonewton force per length squared times length to the fourth, right? Okay. So EI has units of kilonewtons per meter squared, right? And that's why I kept the kilonewtons downstairs here, kilopascals. So right, this has units of kilonewton meters squared. And so this is going to have units of kilonewton meters, right? So that's consistent. And then that's going to give you the deflection in meters, right? So, okay. So let's do the numbers. Okay. So this evaluates to 114. So I get 114 over the 200 to the 6 times that, right? So 200. So over 982. And that gives me, or actually, I get a negative here, right? So I'll get negative 0.116 meters, right? And so that's the deflection at point C. Okay. So, like I said, it's a, unfortunately, because the boundary conditions can end up either on the slope equation or on the deflection equation, you can't always directly get the answer from each level of integration. So in this particular case, we had two boundary conditions on the deflection, right? So that required us to basically carry the one integration constant from the slope down to the deflection, right? Also, remember, you have these continuity requirements of the functions at the points, right? So that you know, when the equation has to split because you have a jump either in the force or the moment or something like that, right? You'll get an extra integration constant, but the extra integration constant can always be found by continuity. All right. Okay. So yeah, so you can see beam deflection calculations tend to be a little bit more involved than just, you know, like when we figured out that the deflection for an axial element was PL over AE, right? So in comparison to the calculation for the deflection for axial or torsion, beam deflection is, you know, a little bit more involved. Okay. As a result of that, people have gone about and computed beam deflections for some general cases, right? So let's stop sharing here. Let's see if I can pull up my slides again. And so actually, I'm going to talk a little bit now about beam tables. Maybe I can find them. Maybe. All right. Where's Zoom? Where did Zoom go? There it is. All right. Okay, so here are my slides again. Let's go to where I wanted to. All right, let's the cobble. Can we get to that point? All right. All right. So this is Appendix C in your textbook, okay? And I also posted a PDF on Blackboard, which has a couple of additional cases. But here you can see they've taken some pretty standard cases, pinned at two ends with a center load. Here's the same case, but the load doesn't have to be in the center, right? Here's pinned at the ends, but there's a moment applied. Pinned with uniform distributed load only partially over it, right? And then we have several cases for built in on one side, right? And then there are other ones that even get more involved in that. But you can usually identify one of these cases or use some combination of the two cases, and they directly give you the equations for the maximum slope, the maximum deflection, and also, in this particular case, they give you the equation of the elastic curve, which obviously you can use to compute the max deflection. And you can also just take the derivative of this and get the slope curve pretty easily, all right? Okay, so for example, in the previous example, right, where we had the following, we had a beam that was fixed that was pinned at 2 points and then had a 6 kilonewton force acting outboard on it, where this was 2 meters and this was 1 meter. Excuse me. You know, you could be tempted to look at the beam tables to solve this. All right. So when we do that, right, this looks, you might be tempted to use this one, but unfortunately, in this particular case, right, the load is actually inside the pinned element, right? So it's not quite the same condition. But what you can do is actually, and usually this happens, you can be a little bit clever, and you can recognize that actually this case, where we have the moment applied at the second pin location, is equivalent. If we think of this beam case here that we just solved, and we truncate it, so it's only used considering points A and B, and now we're going to move this 6 kilonewton force onto point B, so that gives me a down force there of 6 kilonewtons. But that really doesn't do anything because it goes right through the pin load, but it also has to add a bending moment here of 6 kilonewton meters. So now you can see that that case is exactly the same as this case here, right? All right. But so that you can actually use that, and you can get the deflection that would happen here, right? Oh, and I have, yeah. So actually, you see the moments going the other way. So actually, the deflection would go like that, right? So go like that, right? Okay, which isn't bad. But remember, what we really wanted to find is we wanted to find the deflection right here at point C. So if we do this, although this is the correct case, it doesn't give me the deflection at point C. So how could we deal with that, right? Well, actually, again, if you look at this a bit more closely, you can consider this case here, all right? And that's almost like what would happen from point C outwards. Let me just talk about it a little bit, and you'll see what we can do. So here's A, and here's B. And now we're using that case where we have the moment here, right? All right. Now what's happening from C to B, right? Or I'm sorry, from B to C, right? We have a down force of 6 kilonewtons, right? And then at this point B, we have a reaction moment going in the opposite direction, and then the 6 kilonewton acting up, right? All right. So in a sense, that would be the same. If you look at it, right? This is exactly the same type of support forces we would get if we had it built in. All right. If we consider this case, right, we have it fully built in at point B, and this is point C. So in fact, the reaction forces we get are the same from either situation, okay? So from a loading standpoint, from point B to C is actually the same as the built-in case, with one minor exception. It's not quite built in. The whole thing is rigidly rotating because, right, we have this deflection curve here, so it goes like this. So point B from the first case has a rotation at B. So really, it's this case here, but rotated by theta B. So in fact, the case from B to C really looks something like this. It's equivalent to the built-in case with the 6 kilonewtons. And the angles are very small, so the fact that this 6 kilonewton, we consider it to rotate or not rotate, really doesn't make a big difference, right? But this angle here, this angle right here, is the rotation angle at B that we can get from that above case. All right. So it's a couple of steps you have to do, but what you can do is, you know, use two of those cases to get you the actual deflection. So again, go back up. The way I would go about solving this one with beam tables would be consider this case, right? Right here, well, okay, they give you the equation right here for theta 2. So that is the rotation at point B. So we know that the rotation at point B is going to equal m0 L over 3 EI. In this case, be careful. Remember, L is the length of the beam from A to B. So this L here is 2 meters, right? So that would give me the rotation at theta B. Okay, now knowing that, right, I can go down to this case, right? Now here, the L is 1 meter because we're going from point B to point C. We can consider it straight and we can get this deflection, right? This deflection here as calculated likewise, right? So we could use that equation. Again, L is 1 meter, right? P is the 6 kilonewtons. E and I are the same as before, all right? And that's going to basically give me this deflection. But I also have to consider that added on top of that deflection is the amount that it moves down in Y because of that rotation. So this is the amount that point C moves down just from the rotation at theta B, and that value is going to be theta B, right? Or well, if you want, you know, it's approximately theta B times the length, which is 1 meter. Okay. And again, for all these things, the actual rotations are really, really small. You know what I mean, right? So you can use small angle assumptions on all those things. You know, sine of theta is equal to theta. All right. Okay. Now, obviously, you could also have a case that just straight up matches one of these cases. And then obviously you just use the beam case exactly, and it's just totally plug and chug. But every now and again, you have to do some trick like I just explained. The other thing that you might see is you might see a beam loading case that could be, let's say, a point force as well as a distributed load. So let's say you had a case that looked like the following. What can I to draw it. Oh, well, here we go. Here we go. This is an example here, right? So this is on this slide. So let's say we had the following case that we wanted to consider. And we have a beam table solution for the point load somewhere on the beam. And then another solution, maybe from a beam table, where we have a distributed load also on that beam, right? So we could get deflections from this case and this case separately. And because these are linear systems, again, we can invoke superposition and we can just add those two together. So we have, this is from actually the other beam table, but you could compute the deflection from this beam loading case and then the deflection from this beam loading case and just add those two together. And that would give you the solution. So maybe I'll maybe do an example of that. Let's do one that works pretty well. That's a good example. Hold on, let's see. The ones in the book, they take it easy on you. They don't have those. We have to make one up. No, I'm sure we're gonna hear it. Let's do this. The part superposition. Yeah, okay. So let's look at problem 1284. Okay, so I'm gonna escape out of here. I'm gonna stop sharing the PowerPoint slides for a little bit. All right, so I'm gonna clear this out. All right, so let me share my screen if I can. Get back to here. Share screen. Here. Oh, it froze again. Oh, come on, man. Why is it doing this? Shoot. It froze again. All right, let's try this again. Oh, well, maybe I can do this on one slide. Ugh, it froze again. It really stinks. Well, let's see. I'll try to do this on one screen because I can't scroll. Okay, so if we're going to consider problem 1284, right? This is 1284 in the text. So we have a beam that looks like the following. It's an I-beam, right? I'll try to draw like an I-beam, I guess. All right, so it's an I-beam. It's fully fixed on the right-hand side. And then there's 2 point loads here. At point B, we have an 8 kip force. That's B. And then in the middle, at point C, oh, it doesn't give me a point. I guess I'll call that C. We have a 4 kip force. And this is point A, I guess. And then this is 6 feet. And this span here is also 6 feet. And okay, so this is a wide flange beam, a W10, 15. So that means a wide flange beam that's 10 by 15. And there's a stand, you can look that up in appendix, one of the appendices in the book to get the I. I'll look at that in a second. And it's made out of A36 steel. So that means that Young's modulus is going to be the 30 times 10 to the 6th PSI. All right, so we can look up in the book. Let me stop sharing for a second and I'll show you the appendix. All right, I'm not sharing the screen yet, but just hold on 1 second. I have to go through and do 6,000 clicks again. Okay, I always have to do this online nonsense. Type in a bunch of passwords. Wait for things to load. I'll tell you, the only good thing about this COVID pandemic is, before we had this, people used to talk about that we're going to do everything online teaching. The nice thing about this COVID stuff is that I don't think anybody's going to say that moving forward, because online teaching really is terrible. This is really terrible. But anyway, I have no choice. Okay, so this is Appendix B. I know I'm not showing it. Hold on 1 second. Let's wait for that to load, and let me see if I can share the screen now. Where is it? Share screen. God. All right. So here you go. Here, when we talk about I-beams, right? They're standard extruded shapes, right? And so you don't usually make your own custom I-beams, although you could if you had to, but it really doesn't make a lot of sense. So here are some standard shapes, and they say this is a W1015. So that has to do with the width and the height of the beam, right? So you can see, like, if we look at W1015, where is it? I hope it's in here because they put it in a problem. So that, I can't write on here. Can I write on here? Oh, yeah. Well, if you look at the row that says 1015, I guess I can't write on here. You can see that it gives us the dimensions of the beam, and it also gives us I, right? So I about the x-axis. That's what we want. So here it says the I about the x-axis is 68.9 inches to the 4th, okay? So that's how we did that bit. 68.9 inches to the 4th, right? Let's see if we can remember that. All right, so we're back on the screen. So that's the I for the beam, okay? All right, so we want to find the displacement and the slope at point B. So we want to find the displacement at point B as well as the slope at point B. All right, so I don't want to go through and do all the integration again. So I want to look and see if this has some beam tables associated with it. So let's look at the beam tables. So Ken, I'm going to have to click a bunch of things. All right, so if we go to the beam tables, all right, there isn't one that looks like that, right? So it's fixed at one end, so that tends to be these, but obviously in all these cases, we only have 1 point force, all right? But we can use superposition for this case and this case. So we can superimpose those two cases together and get our answer, right? So, okay, fine. So let's do it. The other thing is we have to be, and this one I don't think it really matter too much, but the fact that it's fixed on the left side in the beam tables versus fixed on the right doesn't really change things too much. But sometimes you might have to recognize that the rotations might flip sign, or the loads might flip sign. Okay. All right. So here we go. So let me just draw it real quick on here. right? So if you look at that problem again, we're going to superimpose the first case, which is fixed here. And then we have this length here of 12 feet. And the force at the tip is 6 kips, right? And then we're going to look at this case here and consider superimposing this onto it. Again, L is 12 feet. But now we have the 4 kip force in the middle. All right. Okay. And we're going to add these two together, and we're going to figure out the deflection and the slope at this point. All right. So let's call this case Roman numeral 1 and case Roman numeral 2, and we're going to superimpose those. So for case Roman numeral 1, right, we get the deflection at the tip, right? This is the deflection at, what did I call it? This is actually point B here, right? The deflection at point B for the first case is as given here, right? It's the maximum deflection. So it's minus P. So in this case, P is 6 kips, right? Times L cubed. In this case, L is 12 feet, but let's put everything into inches because the E and the I are going to be in PSI and inches to the 4th. So that's 12 times 12. That's 144 inches. And we're going to cube that. And that's going to be divided by EI or 3EI. So 3 times 10 e to the 6th PSI times, what was it? I forget, 68. I think it was 68, something like that. Inches to the 4th, right? And so if we do that, all right, so I get a deflection here of 8.78 inches. All right, so that's just if we have the tip load. Now we're going to consider if we just have the midspan load. So we're going to look at case 2. And here we would get the deflection at point B, but from load case 2. So here is Vmax. Again, that's obviously going to be at the tip. So this is the equation we use here. If you had to find it at some other point, you would use the elastic curve equation, but we don't have to here. And so that's minus 5 times P. In this case, P is 4 kips, right? L is still 144 inches, and that's cubed as well, over 48 times E, which is 10 to the 6th, and then I, which is the 68 inches to the 4th, right? And this gives us, I should put a negative here, I guess, technically, right? All right, this gives us minus 1.83 inches. So less. So the actual deflection is the sum of those two. So the actual deflection at point B is going to be the 8.78, minus 8.78 minus the 1.83, which is 10.6 inches. Now, obviously, you can get this the slope as well. And to get the slope, right, we would use this equation for case one, and then this equation for case two. The only difference being, again, that we would use 4 kips for this equation and 6 kips for that equation. You could add those two angles together. All right. Okay. All right. So the beam tables are actually really useful, you know. And then actually, if you look online now, there are even like little HTML, JavaScript applet things that'll allow you to draw beams and compute the deflections directly. So it's really not as bad as it used to be having to calculate all these things by hand. Okay. All right. There is one last thing I wanted to cover, and this is right. So if you remember back when we did, do I have slides on this? Oh, okay. I'm gonna have to do it by hand anyway. Okay. So I want to talk about statically indeterminate beams and how we handle that situation. Okay. So let's talk a little bit about this. I'm going to clear this out. All right. All right. So if you remember when we did deflection in torsion and axial, what we did is after we figured out how we could calculate the deflection, that allowed us to solve statically indeterminate problems because remember, we had extra constraints, we had extra reaction forces, and we needed to use some sort of compatibility displacement condition to solve for those extra reaction forces, right? So that's why we needed to be able to compute the deflections, right? So in beam bending, we can have the same situation. So for example, let's look at the following problem. All right, so let's imagine we have the following beam bending problem, right? So I'll put a uniformly distributed load on here, for whatever it's worth. Right? Try to keep it relatively simple. Okay. All right, so if we look at this problem, right, we could start trying to solve this by integration, assuming you can't find a beam table. I don't know. Is there a beam table on this? I probably picked one if there was this beam table. Let's just see. I don't think there is actually, right? Because, yeah, I know there isn't because they don't have any cases where it's fixed on one end and a roller on the other, right? So fine. So at least in your book, this beam table does not exist, right? So let's say we want to find this by integration, right? As we did the other problems, right? So we got a distributed load, and this is length L, and then an E, and then an I, right? All right. So if we look at this beam, we first need to calculate the shear and the moment diagrams, right? So we need to get the reaction forces. All right. So we have acting up here, the reaction force at A. I have a moment at A, and then I have a reaction force acting up here at B. All right, so let's call this A, and this is B. And we have the distribute load, we have the down load, right? So which is known, right? W is given, obviously, right? All right. Well, the problem we have here is we have 3 unknowns, MA, AY, and A and BY. But we can only write sum of forces in the y direction equal to 0, and sum of moments around some point equal to 0. There's only 2 equilibrium equations I can write. I mean, if you try to do sum of forces in the x, you just get 0 equals 0, so it doesn't give you anything. But I have 3 unknowns I need to solve, right? So this is statically indeterminate, all right? So how do we solve these? Well, you could try to explicitly add the deflection condition, right? That, maybe the deflection at point B is equal to 0, right? And then, deal with it that way. But an easier way to do this is actually, the easier way to do this is to use the trick. We talked a little bit about it, the direct force method, the assumed force method. So if we do the assumed force method, you'll find that this works out easier, okay? So instead of trying to solve this in one step as we did with the direct approach, what we're going to consider here is we're going to relax one of these conditions and make it an applied or assumed force. So I'm going to relax this pinned condition at B, or the roller condition at B, and I'm going to consider the following problem, right? So I'm going to be built in here at A, right? We still have the distributed load. And I'm going to put a unit force here for BY, right? I'm going to take BY. And remember, what we did was we let this go to be a unit force, like 1 kilonewton or whatever it works out to be, right? And then what we want to do is we're going to break this up into superposition, right? We're going to consider this to be this problem. With, oh, don't do that. With the download. Right? So we have that problem, which is no longer statically indeterminate and actually has a solution by the beam table. And we're going to superimpose onto it the following case. So we're going to consider the superposition of these 2 cases here. Okay, well, now we have the force acting. All right, this is my unit force. All right, so we know that the deflection at point B, I should not use that. I should use B, right? We know that the deflection at point B has to equal 0. So case 1, case 2, right? We do the beam deflection case here. If we look at this case, in fact, you can see that I won't flip it back, but you can, if you look at the appendix C in the textbook, you will see that from this case with the distributed load, the deflection at point B from case 1 would be given by the following relationship: minus PL cubed over 8EI, right? All right, so that's the deflection at B. It's going to kick down, right, like this. Now, what we need to have happen is we need to consider this case where it kicks up, and this deflection here has to be the opposite of what that deflection is. It has to be such that, it makes the net deflection at point B go to 0, all right? And so that's why we use the unit force there. Okay. So, all right. So I'm going to call this, let's not use P. Let's use F for now. Okay. All right. So now if we look at the load case with the point load, the deflection at B, I'm sorry, not B, right, I say B, all right, A. B, due to load case 2, if you look this up in the beam table, this is going to be FL cubed over 3EI, right? 3EI. And I dropped the minus sign because the force is going up, and that means it's going to flip it up. So we need F such that this term is equal to the negative of that term, right? All right, so we want FB, right? If we add those two displacements up, we want that to go to 0, correct? All right, and so if we do that, then that means that, okay, minus PL cubed over 8EI plus FL cubed over 3EI has to go to 0. All right. And now, like you can see, the L cubes cancel out, the EIs cancel out. And now I can get that F equals 3/8 times P. So that means that for the deflection at point B to go to 0, so that there's a roller, the reaction force at F is actually 3/8 of P. And what am I doing? Oh, what am I doing? Why am I doing this? I did this wrong. I have this 8. This is not P. Ugh. I am so out of it this semester. This is W. I'm sorry. Because this, I wrote down the wrong equation. I'm sorry. So let's do this again. All right. Same concept, right? But I wrote down the wrong equation, right? Obviously, this is a distributed load force. So here is the, for the first case, that's the deflection at point B due to the distributed load. So that means that actually this here needs to be the following, right? Minus WL to the 4th over 8EI. And if that's the case, well, okay, fine. So the EIs cancel out, and then if we divide by L cubed, I just get left with 1 L there, and now I get F is equal to 3/8 W times L. Okay, so that means that we now know what the reaction force is at that point. Okay, so like in terms of W and L. Now, in this case, right, if we look at the, we can figure this out. For case 1, the reaction forces at point A for case 1 are going to be as follows, right? The up force here is going to be W times L, right? That's the shear force there. And the moment, this way, so the moment is, right, it's going to be WL squared on 2, right? Because this is like a point force acting down at the middle, L on 2 of W times L. So that would be the moment in that case. In this case, right, the shear force is going to be F acting down, which we know is L on 3 WL on 8, right? And then the moment that goes that way, this is going to go this way. And the moment here will be F times L. All right. So now I actually know the reaction forces for the total case because it's these added together remembering that F is 3/8 W on L. So actually, we've now solved for the reaction forces for this statically indeterminate case. So here we have the down force of W, the distributed load. Acting down is W. All right. And the reaction force on the right-hand side is F. So we know that's going to be 3/8 W times L. And then the reaction force on the left-hand side is going to be the sum of F and WL. So F is 3/8 WL. So we add another WL on. That's an 8/8. So that means acting up here, we have 11/8, right? And then we add these two moments together. Now they're actually acting in the opposite direction. So this, if I put in FL, if I put in WL3, this becomes 3/8 WL squared. And they go in the opposite. So what's bigger, 2 or 3/8? Well, W over 2 is bigger than 3/8 W. So that gives me a net force going this, I'm sorry, net moment going this direction. WL squared on 2 is 4 WL squared on 8, and then 3. So this is a WL squared on 8. All right. And so those are the support forces. And we were able to figure them out now for the statically indeterminate case. And the way we did that is because we know the deflections. We're able to compute those. In this case, we used a beam table, right? So that's why one of the reasons why it's nice to use a beam table. It makes that calculation a little bit easier. Okay.